Welcome to this explainer. Today, we're diving into a real-world legal defense that literally reads like a sci-fi novel. We're going to look at exactly what happens when traditional law collides head-on with complex system science, statistical physics, and network theory. And incredibly, it's all over a single retweet. It's a fascinating case that perfectly captures the friction when our modern network realities crash right into our traditional legal systems.
All right, let's take a quick look at our roadmap. We're going to cover 1. Law meets complex science. 2. The scale-free network. 3. CAP theorem and chaos. 4. Avalanches and criticality. 5. Fluctuation versus phase transition. And finally, 6. A clash of paradigms. We're going to systematically break this down and see how the architecture of the internet itself was essentially put on trial. Let's jump right in.
Section 1. Law meets complex science, the core conflict.
So to really grasp this conflict, we start with the case of Dr. Chen Jingyuan, whose single retweet was legally accused of causing a serious disruption of public order. It's a striking premise, right? Just one click by one everyday individual being held legally responsible for a systemic breakdown. There is a huge contrast here between a linear legal assumption where one action equals one massive result and the nonlinear scientific reality of complex social networks. The prosecution's logic assumes a straightforward A causes B relationship. But as Dr. Chen's defense argues, a social network isn't a simple machine. It's a highly complex system where outcomes are entirely nonlinear and deeply dependent on the overall state of the network at that specific moment.
Section 2. The scale-free network, zooming into the environment.
To actually understand the scientific reality of a retweet, we have to look at the physical topology of platforms like X or Weibo. In network science, this is often described by the Barabasi-Albert model, basically a scale-free network. In this kind of environment, influence follows a power law distribution. This means influence is absolutely not distributed equally. A user with fewer than 100 followers, like Dr. Chen in this specific case, is mathematically classified as an edge node, possessing virtually zero system-wide influence. Meanwhile, a tiny fraction of users, the hubs, have massive reach.
Just look at the sheer extreme inequality here. An overwhelming 99% of the network are edge nodes. This means they are statistically incapable of disrupting the 1% of hubs that actually hold the whole system together. Without a massive hub amplifying it, a message from an edge node is honestly just a drop in the ocean.
Derived from physicist Reuven Cohen's threshold formula, the math shows us something wild. You could randomly delete millions of edge nodes, and the overarching network structure wouldn't even flinch. Scale-free networks are just incredibly resilient to random changes at the edges. So, the actions of a single edge node simply do not possess the kinetic energy required to shift the entire system.
Section 3. CAP theorem and chaos. The nature of the distributed system.
Let's move to our second scientific pillar and see how computer science explains the default state of these networks. It all comes down to how data physically moves across global servers. The CAP theorem is a foundational principle of distributed systems, and it dictates a hard truth. A global platform must make trade-offs. To keep a social network available and partition-tolerant across massive global servers, perfect consistency is mathematically impossible to achieve. If you want a global platform running and available for everyone, you absolutely have to sacrifice total order.
What this essentially means is that in a distributed network, chaos and disorder are the physical default states. Divergent information, weird delays, and localized unruliness, they aren't glitches caused by a malicious user. They are the unavoidable physical properties of the system itself. Chaos is a structural reality, not a crime manufactured by a single person.
Section 4. Avalanches and criticality. How chaos actually spreads.
So, if chaos is the default, how do massive, system-wide disruptions actually happen? I mean, if edge nodes can't cause them, what does? This brings us to our third scientific concept. Think of a massive sand pile. It is the deeply unstable, critical structure of the pile itself that causes an avalanche, not the 1 millionth grain of sand dropped on top. The system naturally builds itself up into a state of extreme tension. When the avalanche finally happens, it was an inevitability born from the system's own structure, completely independent of the unique power of that final grain.
Statisticians use something called a Galton-Watson branching process to map this step by step. And when we apply it to an edge node's retweet, we see that in the vast majority of cases, the action triggers absolutely nothing. Without hitting a hub, the propagation chain goes extinct almost the exact moment it begins.
In physics terms, when that average branching number, m, is much, much less than 1, your system is in what's called a deep subcritical state. The retweet literally lacks the mathematical momentum to cascade. Triggering a systemic avalanche from that node isn't just unlikely, it's mathematically impossible. It is guaranteed to fade away.
Section 5, Fluctuation versus Phase Transition, Deconstructing the Macro Response.
Now this brings us to statistical physics, which perfectly exposes the flaw of equating a microaction to a macro result. It shows us exactly why a single post cannot be viewed as the sole architect of societal disruption. The prosecution's logic assumes a local fluctuation is identical to a phase transition, which completely ignores the mechanics of how energy actually dissipates in a real system. A local fluctuation is just background noise, but a phase transition, like water freezing into ice or a massive market crash, requires the entire system to undergo a structural shift. They are entirely different categories of physical events.
The fluctuation-dissipation theorem proves that a system's response is entirely dictated by its internal structure and accumulated tension. Toss a pebble into a calm pond, you get a little ripple. Toss it onto a precarious pile of dynamite, you get a massive explosion. The pebble didn't contain the explosive energy. The system did.
So, asking the big question based on everything we've just uncovered, can one single edge node actually crash a complex system? Does the science support this legal accusation at all?
As this quote emphasizes, if a system breaks from a single retweet, that system was already in a critical state of near collapse. The blame, scientifically speaking, lies entirely with the overarching architecture and its accumulated pressure, not the random spark that happened to set it off. If a macro-level disruption occurred, it was purely because the network was inherently unstable to begin with.
Section 6. A clash of paradigms, Newtonian law versus quantum reality.
We've now arrived at the profound philosophical clash at the heart of this explainer. What happens when our legal language is operating in a different century than our technological reality? We have massive friction here. Newtonian legal logic, which strictly demands linear A causes B outcomes, is trying to govern a nonlinear, quantum-level complex network. The law wants to point a finger at one person and say, you caused this disorder. But science tells us that in complex networks, disorder is the baseline, and any large-scale change is a product of the entire system's geometry.
The ultimate scientific takeaway boils down to this equation right here. A macro result is never just the perturbation. It requires a specific system structure and a critical state to amplify it. You cannot simply erase the system structure from the equation and lay the blame on a microperturbation. To do so completely defies the fundamental laws of physics and network science.
Which leaves us with this final, really provocative thought to ponder. Are the legal systems we rely on today fundamentally incapable of understanding the physical realities of the networks we live in? As we move deeper into an era defined by complex algorithms and global connectivity, this tension between linear laws and nonlinear science isn't just an abstract debate. It's an absolutely vital question about how we define truth, responsibility, and justice in the digital age. Thanks so much for joining me on this deep dive. See you next time on The Explainer.